All right, today's quick lecture, we're going to talk about functions and what type of special relationship they are in mathematics. There are lots of different types of relationships between two variables that we can see within mathematics, but a function relationship is a special type of relationship that follows certain rules. The main rule for a function is that each input, x, will always have at most one output, y. And of course you could switch those around, but generally we think of, because all variables of course are just random choices that we're making to represent things, but generally we let x represent our inputs and y to represent our outputs. So let's take a look at this from the standpoint of a machine that we've made that's a function machine. Maybe we built it in our back garage and it does stuff for us, and we're just going to call it a function machine. And we know that our function machine is working good when it gives us a consistent output. So our x is what we're inputting and y is what we're visualizing as our output. Okay? Now, if the function machine is working properly, every time we put in a certain input, we should get a certain output. And we should only get that output. For example, let's say that you took your keyboard and you hit the space bar, but then the output, what you saw on the screen, is that it went back a space. This would mean that something is wrong with our machine. Because if I hit a space bar, I don't want my keyboard to go backwards. Let's say most of the time it does the correct thing. It gives me a space on my document, but then sometimes it goes back. Or maybe it types an 8 when I hit the space bar. If stuff like that was going on, you would say something is terribly, terribly wrong with my keyboard. Because I'm performing the same input, but I'm getting an inconsistent output. Sometimes it's giving me a backspace, sometimes it's actually giving me a space, which I wanted, and then other times it's typing an 8 onto my document. So with that idea, something's wrong and my function is not functioning. And so we would say that that relationship is not a function. Let's take a look at it from another standpoint. Let's say we have some names, and this is my input. So we have Bob, we have Mary, we have Cindy with a Y, and Bill. And we have several ages numbers here. One is, we have a 20, we have a 25, and we have a 32. So Bob is 20, Mary's 25, and Cindy's 32, and let's say Bill is also 20. All right, so here's my inputs and here are my outputs. If you look at the relationship we have here, each input, each person's age, again, putting it into the function machine, gives us a consistent output. And thinking in terms of just reality, and that's one thing that functions are nice, is that they work within real things. If I were actually, looking up these people, these specific people, say on a census report or something, they would only have one age, one birth date given to them. And so I wouldn't ever run into the problem with one person having two different ages. Now, it's okay for two different people, like Bill and Bob, to have the same age. That's okay, as long as Bob is always going to the same age as is Mary and Cindy and Bill, right? So in other words, they're only going to have one age per person. Another example would be the same people, Bill, Cindy, Mary and Bob, and they have student IDs. So I'm going to make these really short student IDs, like 325, 172, 678, and 9, 10, 11. Okay, so anyway, these students, Bill, Cindy, Mary, and Bob, all have a certain student ID. And in fact, they're all going to have a unique ID. And so we don't even have different people having the same ID. This is a special type of function relationship where it goes both ways. This is called a one-to-one function relationship, where not only does every x have exactly one y output, but every y goes to a single x. The previous one we looked at, where it was ages and names, this would not be a one-to-one, because you can see that the 20 here goes to two different people, so it's not a one-to-one relationship where it goes either way. Okay, then let's look at another example here, months and holidays. So we have February here, we have October, and then we have November. And we have Valentine's Day, Halloween, Veterans Day, and Thanksgiving. Now in this case, February goes to Valentine's Day, October goes to Halloween, November goes to Veterans Day and to Thanksgiving. Here's an example where we do not have a function relationship. Why? Because if I type in November, I actually get two outputs and not just a single output. So not a function. All right, so if we've determined that a function, a certain type of relationship between x and y, is exerting and having a function relationship, we can use certain notation to indicate that our relation, our equation, if you will, which what we mostly use in here, mathematically, is a function relation, not just a regular relation. What we do is we take this symbol, f with parentheses and an x, and substitute that for y. We read this as f of x. So, for example, let's say I had an equation here that I knew was a function, y equals 3x plus 2. If I can establish, or if I know that this is a function relationship, instead of y, I could put f of x in its place, and we simply write it like this. So all this does is it tells me, well, hey, this isn't just a regular input-output relation, but this falls into the category of a function relation, where I can be assured that for every x, I'm going to have exactly one y as an output. And so, for example, if I'm asked to find the f of 3, this also kind of falls into that machine that we looked at the very beginning. When we we're asked to find f of 3, basically we're saying put 3 in to the function. So 3 is now my input. So it's kind of like we've put it into this function here. And so over here we would substitute out the x, which was representing our input, and we would evaluate this using the correct order of operations, which of course multiplication comes first, so that becomes 9 plus 2, which is added together 11. So for this relation, the f of 3 equals 11. So notice this is my input, and once we evaluated it, we got the output here. A lot like the function machine. So think of those parentheses as kind of like your, the opening of your function machine. All right, so looking at tables here, we're going to determine whether we have a function relation. If so, we're going to evaluate a couple of things here. First thing we're going to evaluate is the f of 2, where 2 is our input, and then the f of x equal to 4, meaning our input, x, is resulting in an output of 4 for y. And so we want to determine what the x is. All right, so looking at our first thing, we have a 2, 4, 2, 4, and a 6 here for my inputs, and then my outputs are 4, 7, and 4. So notice one thing is that 6 is giving me 4, and 2 is giving me 4. So the question is, well, if we have that, is that a function relationship? Going back again to what we saw earlier with the months, we can have different months. Okay, wait, that doesn't work. Let's think of it as cities and holidays, or we had people and ages. We can have different people with the same age. You can also think of it in terms of different cities having the same population. And so that does make sense. Remember, functions will always make sense in the real world. And so we would say, yes, this is a function. It follows a relationship. Each x has a consistent y. Now, even though the y's are similar, or the same in this case, that's okay. We can have different x's giving us the same y. We just can't have the same x giving us different y's. Again, you can go back to the keyboard example as well. You don't want your input, your keyboard, the button you hit, to give you different outputs every time you hit it, right? The 2 and the 6 represent different hits, but the same outcome. So maybe you hit the left arrow button or you hit backspace, right? They both result in the same thing. All right, let's go to the second one here. We have 2 giving me 7, 4 giving me 5, and 4 giving me 4. All right, so 4 giving me 5 and 4 giving me 4, that's a problem, because 4 is not giving me a consistent output. And so because of that, we would say, no, this is not a function, because my x's are not giving me a consistent y. And then the very last one, we have 2 giving me 7, 4 giving me 5, and 6 giving me 4. And in this case, like, there's nothing repeating, and so there's not even really a question. We would say, yeah, this is definitely a function. So the thing you want to look for when we're deciding whether something's a function or not is repeating x's giving us different y's. That's really what you want to find. All right, so now going back, for the first one, we're asked to find the f of 2. In other words, if we have an input of 2, what is the output according to the function? And in this case, the output is 4. So the f of 2 is 4. This is not a function, so we can't really do that here. And here, the f of 2 for this function is, yes, you guessed it, 7. The second thing they want us to find is the fx of 4. That means the output is 4. What's the x? And for this one, where the f of x is 4, we have 2 inputs, 2 x's, 2 and 6. Again, here we don't have to worry about this. And remember, it's okay for a y to have 2 x's, just not our inputs or x having 2 y's. That would be like 2 different cities having the same population. That's doable, but you can't have a single city with 2 different populations. And over here, for f of x equal to 4, we see that x is equal to 6. 6 is the input. That gives me the output of 4. Okay, so when we're looking at graphs, we actually have an easier time deciding whether something is a function or not. I'm going to give us three different graphs here. One's a parabola, the other might just be a line, and let's do the third one as a sideways parabola. Okay, and there's lots, of course, of other functions you can have. I'll even draw one up here. Let's just do one that looks like this. So when we're looking to see whether a graph is representing a function relationship, we can do something called the vertical line test. The vertical line test is where we could draw a vertical line, and if we can draw a vertical line, it only passes through a single point, anywhere on our graph. So let's go over here to the parabola. If I could draw vertical lines anywhere along here, the question is there any place where it crosses the graph more than once? And we see for each one of these that, no, for every vertical line we can draw, it only passes through the graph at one point. Vertical lines are what we get when we have x equal to some number c. If ever you're asked to graph x equal to some number, a constant, 3, x equal to 4, x equal to 5, that gives you a vertical line, because on this line, all the x's are that particular number. Right? So this may be, let's say it's 4, 4. And maybe this right here is 4, 3. And this one is 4, 0. But notice that all the x's are the same number, 4. So x equal to 4 would give us this vertical line. So when we draw a vertical line, we're saying here's our input of 4. If it only passes through one point on the line, that means there's only one output, one y value for a given value of c. For each one of these, you can see then, in this particular case, almost all functions. But when we come down here, notice with my sideways parabola, this 1x is giving me multiple inconsistent y's. Say, for example, this might be 2, 4, and this might be 2, -4. Either way, we have the same input giving us an inconsistent or different y outputs. That would mean this is not a function. But up here, again, all the vertical lines we could draw pass through only a single point, and so therefore this is the only one here that is not a function. The rest are functions. In fact, we can use the graph to kind of help us discern what the inputs and outputs might be for a function. For here, if we were asked to find the f of 5, I'm sorry, I wrote that wrong, but maybe we'll come back to that. Actually, I actually want to find the f of 5. F of 5, notice, remember, that what's inside here is my input or my x. And so along my graph here, I would want to go to where x is equal to 5, which is right here. And then we want to move up along the graph till we see what the resulting y is that goes with that x. In other words, this point here has 4 as an input. 5 as an input. What is its output? And the answer is 4. And so the f of 5 is equal to 4. on this particular graph. And so what would the f of negative 2 be? Well, if we go to negative 2 again here along my graph and go down, we can see negative 2 is equal to negative 5. Now actually I just kind of picked that closely. Actually I think, let's see, negative 2 is actually going down to, it looks like negative 6. That may be off there a little bit. It's hard to tell on a graph, but sometimes, unless you have a calculator or some sort of technology, there are points where it appears where it's actually hitting one of those intersections. Until it's not fractional or decimal. So that's what we can do on a graph. This can also go the other way. If f of x is equal to, say, negative 1, what's the x? So remember, f of x is our symbol for y, so it's saying where is y equal to negative 1. So looking along our graph here, y is equal to negative 1 right here. In fact, it appears to be the y-intercept, where it's crossing the y-axis here. And so we have to ask, well, what is the x here when y is equal to negative 1? And if we go up, we can see that since we're on the y-axis, the x value is 0. Negative 1, 0, 1. So at x equal to 0, we have negative 1. Again, the ordered pair here would be 0, negative 1. Input x, output y. All right, now most of the time what we're going to be doing is looking at equations. So I want to just run a couple of examples here where you're given a function and you want to find f of this or f of x equal to that. So for f of negative 3, that of course means we're plugging negative 3 in for x. So negative 3 is my input. And so as you're rewriting this and you want to practice rewriting these, the way I recommend you do this, I'm going to take a step back here, is to simply rewrite the expression, putting a parenthesis where the x or the variable was. Okay? And then whatever this is, that's what we, after we've written it out, plug in here. And this becomes especially important with negative values and such, because negatives can get a little tricky sometimes. So trust me in doing this, practice writing it out, and then follow the order of operations to evaluate this. We first, of course, will do the multiplication, PEMDAS. Please excuse my dear Aunt Sally, where multiplication is always done before addition or subtraction. All right, so that gives me negative 6 minus 5, which is negative 11, because negative 6 minus 5 is the same as negative 6 plus negative 5. We can rewrite every subtraction as an addition as long as we change the sign of the number that follows it. That's just for us to visualize that. So negative 6 plus negative 5 is negative 11. The second part says find the f of x of 7. So that basically is saying substitute 7 for y. So instead of f of x, I'm going to put 7 in its place. So I substituted that out. And now we have to solve this for x. In other words, we want to get x by itself. So the first thing I would do is to add 5 to both sides. 7 plus 5 is 12. So we have 12 equals 2x. And it's 2 times x. So if I want to undo that multiplication, this of course became 0. So I have 2x is equal to 12. Another 2 times what is 12? To systematically find that, we can undo our multiplication by 2 by dividing both sides by 2. 2 divided by 2 is 1, so that cancels out. And I have x equal to 12 divided by 2, which is 6. So in other words, the input of 6 results in an output of 7. And we could see that here. If I plug in 6 and find the f of 6, that's 2x, or 2 times 6 minus 5. 2 times 6 is 12, and 12 minus 5 is 7. So that checks. On a graph, the input of 6 gives me an output of 7. Also, the input of negative 3 gives me the output of negative 11. Okay, and let's do another one here. With, we want to find the f of negative 3. So, for this function, I'm going to rewrite it. Again, putting parentheses where I see. So if I have parentheses within parentheses, I'm just going to go ahead and change that parenthesis to a bracket so we can discern. And it's blank minus 3. So you can see I turned these parentheses simply into brackets. And now I'm going to input the negative 3. Okay, so I'm going to do my innermost parentheses here, negative 3 minus 3, which again, oops, I'm going to change that to plus negative 3. So negative 3 plus negative 3 is negative 6. And then we have this 2 out here. So I'm just rewriting this. So we did the operations within parentheses first. We combined those two. And now I'm going to go through and do all the multiplications. So there's 2 multiplications here. So this becomes negative 15. And I'm going to make this plus negative 2 as well. So we have plus, and then the result of that multiplication, negative 2 times negative 6, is positive 12. 2 negatives multiply, give me a positive. And then negative 15 plus 12 is negative 3. And so the f of negative 3 is negative 3. Strangely enough, negative 3 is the ordered pair that we have here. And I'm seeing that actually I did the wrong things here. I was using the same inputs as the previous one, so this is what I just did here. We could do the same thing with 5, but let's go ahead and go over to the f of x of 2. So again, I'm going to take out the f of x and put 2 in its place, equaling 5x minus 2 times x minus 3. Now there's a lot going on here, so I'm going to do some erasing. So I give myself some space. Alright. And in fact, I'm just going to rewrite this. Okay, so again, we're putting in 2. 5x minus 2x minus 3. Okay, so first off, I'm going to make this a negative 2, which when you see the minus in front of it, you can just think of it as a negative, but just to make it clear, again, change it to a plus as long as you change the sign of the number that follows it. It was minus positive 2, so I'm making it plus negative 2. Now I'm going to distribute this to get rid of the parentheses. So that gives me 5x plus negative 2x, and then negative 2 times minus 3 is positive 6. We'll combine like terms that are on the same side of the equation. So that gives me 3x plus 6 equaling 2. Subtract 6 on both sides. That gives me negative 4 equals 3x. And now to solve for x, we divide both sides by 3. So we see that x is equal to negative 4/3. So an input of negative 4/3 gives me that output of 2 for that function. Lots of practice there for some of the problem solving, equation solving things that you've learned in the past. This is the basics of functions as formulas, as graphs, and it's just a simple relationship where every x has at most one output y.